Okay, here we go. So this idea of constant rate of change is really the core idea of calculus. Incredibly important. It lays the foundation for being able to understand calculus, because it's one of the fundamental ideas in terms of how quantities change together. Constant rate of change is it's a basic but loaded with a meaning and loaded with different ways of talking about it and looking at it. Okay, and then it's our springboard for understanding calculus. So we want to take some time today to in the homework. So let's review meaning of quotient. So if quantity A is a value of 17 and quantity B has a value of 5, what's the meaning of 17/5, which is the value 3.4 in terms of the quantities A and B? So I've got 3 that I'm about to list. So have a conversation with the person next to you and see if you can come up with 3 ways to interpret the number 3.4 in this situation. Go ahead, see if you can come up with it. Let me just qualify. So this has nothing to do with changes in quantities. So this doesn't really, we're not really talking about constant rate of change. We're just reviewing quotient. Okay, go ahead. Just reviewing quotient. It doesn't have to do with changes. Okay. Where's Quing Hong? Is there one way you could tell me to interpret the number 3.4? Can you just tell me one way that you talked about?
One way?
Yeah.
A is 17.5 times, is 17.5 times of B.
Okay, so you're saying that A is 3.4 times as big as B.
Yeah, 3.4 times as B.
What do you think about that? A is 3.4. Is that a way to interpret that number 3.4? Yeah, good. All right, where is Christopher Bentecourt?
All right.
Tell me, do you think of another one? Just come up with another one. So the meaning of 3.4. Where's Aaron N? The meaning of 3.4. So we got that it's 3.4 is how much greater A is than B in terms of how many times greater it is. Okay, that's kind of saying the same thing. It's true. But it's kind of saying the same thing. Anybody? What's the different one that we had? Jonathan.
3.4 is the measure of A in terms of B.
Measure of A in terms, like as a unit of B. Right? So if you use B as the unit and measured A, you'd do 3.4 of B to get A. That's right. All right? And there's one more thing we said. Maybe the most important one. Somebody else. What is the number 3.4? Tell me your name again?
Jonathan?
Jonathan, number 2.
Is it it's relative size?
Relative size of?
A.
Right. So it's the size of A relative to B. It's the size of A relative to B. So that's the first one I put. 3.4 is the size of A relative to B. It's the measurement of A in the units of B. And 3.4 times the size of B. And so when you start thinking about these, you realize they're all so close, right? They're all almost saying the same thing, but they're subtly different. So that's why we want to think about all 3 of them, because they are subtly different. Okay, any questions? That's kind of review of the meaning of quotient. Okay? Okay, I'm gonna go. Ready? Here we go. So, suppose the container has some water in it. Every additional 40 milliliters of water poured in the container causes the height to increase 7.5. So if you find the quotient 7.5 divided by 40, 7.5, you get the number 0.1875. Okay, interpret that value. Go. What does that value mean? 0.1875.
Yes, since 7.5 is the first order, it's the size
So that's just like the last one.
Okay, Jamal, any idea?
0.1875 is the size of
Okay, so it's the size of it's the magnitude of height relative to the volume in the container. What do you guys think about that? Yes, I heard a no. This is Ross.
It's the size of the change in height.
Okay.
The size of the change in volume.
Are these values 7.5 and 40? Are they amounts of height and volume? And he's saying there are changes in height and changes in volume. So now I'm going to see nods. Okay. I saw the whole class go like this, and the whole class. All right. So right. So these are changes. So the change in height is always 0.1875 times the additional whatever added volume you have. And so we use this. Most of you have probably seen it before, but if you haven't, delta means the change in the quantity, which is actually a new quantity, right? It's a different quantity than, so we make sure we're distinguished between, height versus change in height. We're going to really understand the difference between those, right? So in this case, height is just measuring from the bottom of the container how high the water is. A change in height, how is it different than that? So how would you explain a change in height in this context?
It's like when you add the 40 milliliters, it goes up 7.5, so from where it was from, it went up.
Right, so it's not a measurement of a height, but it's how much additional you add in, okay? Same thing with volume and change in volume. So volume is just a total volume in the container. Delta V is a new quantity that means what? How much the volume changes, okay? All right, so if the change in height is always 0.1875 times the added volume, can we interpret it a different way? Where's Mark go? Can you do it a different way?
could say, could you say the change in height is 0.1875 times the volume? The change in volume?
Yeah, so that's what that one is, right?
Oh, okay.
So the change in height is always 0.1875. So that number 0.1875, can we?
So 0.1875 is the measurement of the height in the units of the volume.
Is it height in?
Or is it the other way around?
Okay, what do we think? Where is Kevin? Chime in here. What do you think about what he said?
I didn't really understand what you said.
Okay.
What I think it is, it's the change in 0.1875 is the change between the height and the change in volume.
The change between the two changes.
Well, not between, but
Yeah.
it's proportional to the change of height to the change of volume.
Okay. All right, so where's Christopher Noriega? And
It's that represents like the amount of centimeters per milliliter.
the amount of centimeters per milliliter, 0.1875 centimeters per milliliter if we're adding water.
Lots of milliliters per something. Because every
And
addition.
for every 1 milliliter, it's 0.18.
For every 1 milliliter, yeah, I think it's the other way around. No, I like what you're going for. But so what is that? Is it milliliters per centimeter or centimeters per milliliter?
Centimeters per milliliter.
Yeah, it'd be centimeters per milliliter. So that would be how much the height goes up per 1 milliliter added, right? Yeah. Okay. Also, relative size, right? Relative size. 0.18 is the size of the change in height relative to whatever change in volume you put in. So if you put in a change in volume of add 1, your height is going to go up 0.1875. That's times as much as that. And so again, so close to the previous one. So now we're talking about changes. Okay, now we're talking about changes, and we have this constant ratio of changes. Right, this is the constant ratio of changes, and so that is our constant rate of change. That's our constant rate of change. How much the height goes up per unit of volume added. So how can we talk about that number in terms of h and v rather than in terms of the changes? Can we even though we know that's a constant ratio of the changes, can we interpret that number in terms of h and v?
No.
I saw a couple of no's. Anybody think you can? Want to give it a try? Yeah, Clint.
Well, you could add H and V into the equation instead of having it be delta H and delta V, because it would be like H, the final height, plus an additional height.
Okay.
So you could just expand delta H and delta V to have it, instead of being delta H, delta V, have it actually have those variables in it. But otherwise, it's not, that number only works for the change, and it doesn't really have a relevance to H and V by themselves.
I'm glad I asked. Okay, so let's see. I'm glad I asked. Anybody else want to chime in here? Yeah, is it? Tell me your name. Janae.
We could say that 0.1875 is the measure of volume.
Is it the measure of volume in terms of height? Is it the measure of v in terms of h?
Oh,
Isn't the other way, it's height per volume.
no, it's a change.
It changes the volume.
Yeah, so it's because we don't know how much started in there. So if you're, so you can't do that because, and that goes back to the question that number 8 in the homework. Does the changes being proportional guarantee that the actual quantities are proportional?
I'm going to say yes, because for any given volume, you can find an appropriate height, but using that changing rate there,
Okay.
1.1875.
Okay, but does that mean that h and v have this is the size of the magnitude of height constant at 0.1875 relative to the magnitude of v? Ross?
I'm gonna say no,
Okay.
because if you have like a certain amount already in there, like you add to it, they're not gonna be in proportion to each other.
Okay. Right, so what if when there was when there was 10 centimeters, so when the volume was 10 milliliters, okay, the height was 5 centimeters to start with. Okay, so let's just take some ordered pairs here. This is a good question. So what comes first? Volume comes first, and then height comes out. So we got 10 and 5, and so we're going to add 40, right? We're going to add 40, so how much was the volume? 50. What's the new height? 12.5, right? We're going to add 40 more. What's the new volume? What's the new height? 20, right? Is the relative size of H to V constant? What's the relative size here? 1/2, right? What's it now? Is it 1/2? No, less than 1/2, right? That's actually 1/4, is that right? What's it now? 2/9. You see? So this is, and we'll see this again some more on Friday. But just because constant rate of change means the changes the changes are in this constant ratio, okay? But that doesn't guarantee that your actual quantities will be in the same ratio. Back to my question: can we interpret the 0.1875 in terms of H and V, like with a statement like we're making here? Can you say what that 0.1875 is? Anyone thinking that we can? Because we can. Yeah.
If you make assumptions about where the height and the volume started out, you said that they both started out at 0, then 1.75.
Okay, so you're back to this question that it is. Okay, so it's kind of halfway in between. So every time V changes by 1, H changes by 0.1875. Is that right? So how is the quantity H changing relative to V? How is the quantity H changing relative to the quantity V? So do you see how I'm talking about H and V now? How is H changing relative to V?
But it's still a change in the quantity and not the quantity itself.
Okay. True. That's right. But how is H changing relative to V?
Okay, 0.1175, or 0.1875.
So 0.1875 times as fast. Times as fast. H is changing this fast relative to V. So it's kind of in between, right? So you have to have that change in H and V, but I'm still talking about the quantities H and V. I'm not talking about the changes. I'm talking about these numbers here. Do you see? So I'm talking about how V is changing, or how H is changing relative to V. H changes 0.1875 times as fast as V changes. So I'm talking about the quantities V and H and using that 0.1875 to do it. Is it okay? Does it make sense? H is changing 0.1875 times as fast. The values of H are changing 0.1875 times as fast as the values of V. Okay, so just, if it's not perfectly 100% clear, it's okay. Well, we're going to come back around to it many times. Okay. Yeah, question?
I just had a breakthrough in my head.
Can you explain it? Yeah, that's great. Share it with us. That's what we need, breakthroughs.
I just kind of looked at it with the arrow as well. 10 plus 40 is 50. 50 plus 40 is 90.
Okay.
And those changes are happening at the same time as 5 plus 7.5 is 4.5, and 12.5 plus 7.5
Right.
is 20.
Nice.
So you just have to compare the 40 to the 7.5 that it already gave you. So these are changing by, the volume is changing in increments of 40, and the height is changing in increments of 7.5. So that's why it makes sense that it's changing 0.1875 times as fast.
Yeah, and so and we don't need to have these numbers. So I could say 490. Okay, how much does the height change? So now, how much will the height change from 20 now? Say, you said.
530.
Why 75?
The difference between 490 and 90 is just 400 milliliters.
Okay.
So for every 40 milliliters, you have 75. So you just scale up 7.5 by 10.
Okay. So what's the new height?
95.
95. Did you catch that? So now the change is 400. So how much will the height change when the volume changes by 400? 75. So still, it's still the height is changing still 0.1875 times as fast as the volume is changing. Okay, any other comments? Okay, good job over here. That was good. All right, so 2 parts of the idea of constant rate change. You got to have 2 quantities changing simultaneously, right? And what's the big idea? The big idea, we went over this in your quiz. Changes in one quantity are proportional to the changes in the other. Okay? And if that's true, then our change in y is always a constant multiple of the change in x. Every change in y is a multiple of its corresponding change in x. And we also said every change in y has the same size relative to its corresponding change in x. And what is that relative? What do we call that relative size? Okay, and what is that?
Constant rate change.
That's the constant rate. The relative size of the change of one to the other, to the change of the other, is our constant rate of change. This is what we're going to see over and over and over again, all semester long. This builds up both. This principle is just permeates both sides of the coin in calculus. And if you remember on the first day, we talked about calculus is really 2 different questions, 2 different sides of the same coin. This idea permeates both sides of the coin. Changes in y are a constant multiple of changes in x. Okay? So before we've used the bars just to mean quantities. Now here the bars mean changes. Okay? So if this is the change in y and the change in x, then where is y and where is x? We're in this, how could you imagine or conceptualize where x and y are in this bar diagram that now these bars are representing the changes?
Somewhere before there.
Okay, right.
Started.
Yeah, so like out here, so we had some amount y from here to here, and that was, and then we had a change in y, and maybe we had some amount x like this, and then we had so x and y had these same corresponding values, and then we saw a change in y and a corresponding change in x. Or the other way around, we had a change in x, and there was a corresponding change in y. Okay, so here's a diagram that shows, the second diagram shows a smaller change in y and a smaller change in x. So they're clearly different. You've got a smaller change in y and a smaller change in x. But is there anything that's the same about those two? Ryan?
The proportions look the same.
Okay.
As far as, relative length at the top compared to the relative length at the bottom.
Right. So what do you see as the relative size of change in y to the change in x? So can we estimate that?
1/2.
1/2. The change in y to the change in x is 1/2.
Sorry, no, 2/1.
2. Is it 2? Let's do a little better than that. What would you say? What's the relative size of changes in y to changes in x here? I just want to do a little more precise than 2. 2 1/4. So how about 2.2? Okay. 2.2. That's just a guess. Okay. So it would take 2 and a little bit more delta x's to make delta y. Okay. Does that hold here? Yeah. Does it hold here? Yeah. So we can have a different change in x and and obviously a different corresponding change in y. But constant rate of change means that that relative size of the changes is maintained. So in all these cases here, delta y is about 2.2 times delta x. Okay, so there it is again. So this every change in y is a multiple of its corresponding change in x, and that multiple would be 2.2. Every change in y has the same size relative to its corresponding change in x. So the size of that relative to that is 2.2. Okay, so this is like your homework problem. Car goes under a bridge, travels a constant speed of 72 miles per hour, meaning that the number of miles it travels for some period of time is always 72 times the number of hours for that period of time. What's delta y? What's delta x? What's k? Go. What's delta y? What's delta x? And what's k? And then while you're at it, how about just y and x? What are those? What would y be and what would x be?
Yeah.
Zoe, you're up. How about change in y?
Change in y would represent the number of miles the car has driven since it passed the bridge.
Delta y is the number of miles traveled since it left the bridge. Agree with that? You don't agree, Chloe?
Because you can start at the time of the distance of 20 minutes after it passed the bridge, and the k value would still be proportional to the change in time. So the delta y is just a change in distance.
Okay, so what in this paragraph is delta y?
The number of miles it travels for some period of time. Like it's going to be after it passes the bridge, so that it's going at a constant rate of 72 miles per hour, but it doesn't have to necessarily start right when it passes the bridge.
What do you think about what Chloe's saying? So, do you agree? Does it have to start at the bridge? Okay, what about the quantity y?
Well, I said that the quantity y would be what it drove before and after the bridge added together. Total of the mile.
Okay, so y is, we've got a starting point and we've got a distance traveled.
Right.
And then delta y is any change in that number. So delta y could be the distance traveled since what? Going to the bridge, right? So that's what you said originally. That's actually y, because it's a distance traveled from a starting point. Delta y then can be any change after that, any change that we want. Okay, what about delta x? Where's Juicy? Delta x in this paragraph.
It's the
So, so what time? The time since it's gone under the bridge? Or just the period of time corresponding to this number of miles? Yeah. Again, any change in time starting any time after going under the bridge. And what's K? Where's Molly? Molly. What's K?
K is just whatever proportionality makes that true.
And what is? And do we know what that is?
72 miles per hour.
Yeah. See, so what would we say? That the big idea here is that this equals, and that's exactly what the statement is saying. It's saying that the number of miles it travels is always 72 times the number of hours in that period of time that it traveled, and that change. Does it make sense? Anybody have a question? Okay, try it again. Same thing. Oh.
Oh, yeah, because it's just saying delta y in this case. It's just saying. We don't know. You could just say the final.
So the number from the first one, the number of miles it travels is always 72 times the number of hours. Constant rate of change. Whatever number of hours you have, multiply it by 72, that'll give you your change in distance for that number of hours. Okay, so in this case, Ryan, you're up. What is delta y?
Delta y would be the change in distance in relation to the original time spent traveling and the additional 1.6 hours.
Okay, can
Well,
you say it more succinctly? What is delta y in this case?
Change in distance.
And do we know that?
Based off of well, I don't know what the while is though. Because if it's in relation to the previous amount of time traveled, and it's a change from that to an additional 1.6 hours, how do you say? I mean, I guess I don't know what the distance would be.
Marco?
Is it 72 times 1.6?
Is it 72 times 1.6? Yeah, so it's the number of miles the cars traveled, how much it increased.
By 72.
Yeah, so how much did it increase? By 72 times 1.6. What's delta x? It's another 1.6 hours. That's a change in time. So that's 1.6. And what's K? 72 is our multiplier to get distance, change in distance from change in time. So, yeah, Kevin.
Should we add units on this? Or?
Yeah, they got the units up here, so I wasn't writing them down. But yes, this is ours. Yeah, always have the units. Yep. And then this miles per hour. That's miles. Right. So again, delta y equals k delta x. Now we know all the values, right? K is 72. Delta x is our 1.6. And there it is. That the number of miles traveled is k times delta x. That's delta y. Okay. Does it make sense? Yes, sir.
If you were to put a value with the, after driving a while,
Okay.
then your change in x would have to be the difference between the amount of time you traveled previously and the new amount of time traveled.
All right, how about this? After driving for 3.5 hours, the car travels for another 1.6 hours. So now what's delta x?
It would be the 3.5 plus 1.6 minus the new 1.6.
Look in it.
Or minus the original 3.5.
Delta x is any change in time, starting any time while you're driving.
Isn't it the final time minus the initial time?
That's one way to calculate it, but it's also an idea of you can just start the clock. You're driving down the highway, you can just start the clock anytime, and you let the clock run and you get a change in time.
Okay, so you're taking
So after driving for 3.5 hours, you drive another 1.6 hours. What's the change in time? 1.6. 1.6. Okay, I want to talk about your assignment and also relate it to what we're talking about here. It's the one that's due Wednesday. Please don't pack up. Yeah.
Can you show us the line statements on chapter?
Yeah, that was.
Yeah. I was looking at the packet, I was like, I don't want to.
Well, it relates to what you did when you graphed before. Why is this going crazy on me? Whoa. Hello. Sorry. Okay. So it's making light. So it's a mathematical program. You know how to. Oh, is the pen? Ah, the button's in the pen. I got it. So it's mathematical. It's not about what's the line segment. What's the line segment command? It's a mathematical program. It takes the mathematics you give it, and it will make an image of whatever you do. So how did we make a part of a curve? How did I make this part of this curve?
So we have to actually add equation to a line. How do you put that to a line segment?
No, that's exactly what I'm saying. It's not that. So how did I only graph part of this curve? I only graphed from what? From 0 to 110. Do you know how to do that? Then you know how to make a line segment. Okay? If you know how to only draw, see this curve, if you let t be any real number, you'll get a whole parabola, right? But we just want to show what makes sense in the context, right? So I'm graphing it only from 0 to what? 110. And you know how to do that from the previous assignment. Making a line segment is no different from that. It's the exact same thing. You see? It's the same thing. There's no difference. Okay? So there's not a line segment command. It's mathematical. So how are you going to create this line and then just show that's part of it? So think about it. Think about it. Okay. And we'll work, but I do want to talk. So here I'm showing our quantity on the x-axis is temperature, and our quantity on the y-axis is attendance, expected attendance. So what am I showing by the purple triangle? This relates to what we just talked about. What am I? So this is temperature. Okay, so this is our temperature, and this is our expected attendance. What is being shown by the purple triangle? Christian?
Expected attendance from this, like 2 certain intervals of temperature. You're talking about the purple line.
Yeah, the purple line. So the expected attendance from 2 different amounts of temperature.
I've read line of that problem. As temperature increases in the calculus triangle, the attendance of the football game also increases.
Okay, good. So as temperature increases, what is that? what is an increase in temperature? What do we call that? Delta T. So this right here is showing a delta T of how much? 10, okay? And then we have some corresponding change in attendance. I want you to estimate the relative size of the change in attendance to the change in temperature. Estimate the relative size of the change in attendance to the change in temperature. Can you do that? What would you say? Mackenzie, what would you say?
Probably just that they're proportional to each other. So whatever delta A is, excuse me, I'm a little sick right now, so it's
Okay.
hard to concentrate
Okay, all right. That's okay. So anyone want to chime in? Estimate the relative size of the change in attendance to the change in temperature. Somebody new. Tell me your name, sir.
Mine?
Yeah.
Connor.
Connor, can you estimate the relative size of the change in attendance to the change in temperature?
I'm a little confused on this whole concept.
Okay, so when we change T by 10, there's a resulting change in expected attendance. Does it go up or down?
Up.
It goes up. So, can we talk about by how many times does it go up? So, by how many times does the expected attendance go up relative to a change in temperature?
About the same.
About the same. Maybe a little bit greater, right? So maybe 1.1. Are we good with that? Does it look about right? Okay, so now I'm going to show you at a different place. Wow. I don't know what is going on? Okay? All right. Now what's my change in temperature now? Up here. Yeah, that's what you're going to do. That's what yours has to do too. What's your change in temperature now? 10. What's the relative size of your change in attendance? Now it's like 0.5 times change in temperature, right? Conclusion about the relationship between attendance and temperature.
Temperature increases.
It is constant rate of change. It is constant rate. Is that right? No. What is it? It's not. The point of constant rate of change is you maintain that constant rate or that multiplier on the changes. Here, your change in attendance is about the same as your change in temperature. But later on, your change in attendance is about half of your change in temperature. So it's a changing rate. You see? It's a changing rate of change. Instead of constant rate of change. I'm glad you think it's easy. Okay, exam is Thursday. Listen up. Exam is Thursday, and then tomorrow, your recitation this week is just study session. I'll be there for the first half hour. If you're in Thursday's recitation and you want to come tomorrow, then you can do that. If you want to come to Tuesdays. All right? But it is required. Come and study, work on the homework. 9 o'clock.
Same room and everything?
I think so. Is she here? Is she still here? I think it's the same room. Is it, Marissa Bell, is it the same room for both recitations? Same room? Same room, same time. Tuesday at 9, Thursday at 9. What am I trying to do here?